Hi, welcome to this video. In this video, we'll be going through Newton's laws and applications of Newton's laws. I'll be using the exam guidelines, the 2021 DBE exam guidelines, to go through the paper 1 section of physics or physical sciences. So let's get into it. So let's say you had a flat surface with a box resting on top of it. And let's say this box has a certain mass, m. So the first thing that we should note is this box, since it has a mass, has a weight, which is a force that pushes it down. And it's indicated by the letter W. So this force, W, its magnitude can be calculated by taking the mass of the object and multiplying it by the gravitational pull. So the weight that is felt on a surface or felt by any object that has a mass is multiplied by the gravitational acceleration, which we know as 9.8 meters per second squared downwards towards the Earth's surface. So the second thing we should note is that this object doesn't move all the way down as it's resting on the surface. It stops at the surface, which means that there's an opposing force acting on it, an equal and opposing force acting on it, that's causing this box to stay in one place, not move upwards, not move downwards. And that opposing force in this case is N, the normal force. And it's defined as the force or the component of a force which the surface exerts on an object with which it is in contact and which is perpendicular to the surface. So if we go back to our diagram, it's the force. So it's the force which the surface exerts on an object in which it is in contact and is also perpendicular to the surface. So next case, what if our box is moving? Let's say this box is moving to the left, in that direction. Now we're getting into the topic of friction. And friction is, let's take for example, you slide your hand across the surface of a disk. How easy or how difficult your hand moves across the disk is dependent on how smooth or how rough the surface of the disk is. If the surface is smooth, it will be really easy to move your hand across the disk. And if the surface is rough, it will be really hard, or at least harder than it was before, to move your hand across that disk. Why is that? That is because there'll be an opposing force acting on your hand on that surface. And that opposing force caused by the roughness or the roughness of the disk is known as friction, denoted by the letter F, small letter f. So if F is 0, then the surface is frictionless, and that means that there is no resisting force that gets applied to the movement and opposes it. But the rougher the surface is, the more friction it has, and therefore it's more difficult for it to move across the surface, which means this force will be higher than it was on a smooth surface or a frictionless surface. So now let's say that in order for this box to move to the left, we needed a force acting on it. So this box, let's say it is pushed to the left. It's pushed to the left so that it can go to the left, and forces that are applied on an object are usually denoted by the letter F, capital F. If we apply the force on this object, it's not always that it will move. Let's say you try to push a very heavy box very lightly. It might not move at first. And why doesn't it move if there's a force applied to it? Well, that's because of the opposing force, the frictional force. But if you continue to increase that force, you might actually move the object. And therefore now, the frictional force is still in play, but it's not the same frictional force that opposed you when it wasn't moving. So there are two cases. There's a frictional force for a static case, a stationary case, which is denoted by Fs. And what stationary or static means is that this object is not moving. So again, it's the case where a force is applied, but you're not moving the object yet because of this resistant force. This resistant force is known as Fs for a stationary case where the object is not moving, and it's equal to mu, which is your friction coefficient, denoted by S in this case, times your normal force. Now, once this force is able to overcome that frictional force, that static force, then we have another case where F is now moving, and we denote it by K. That K stands for kinetic, and kinetic means moving. So now we have a frictional force in a case where the object is moving, and it is equal to the friction coefficient of a kinetic case times the normal force. So these two equations are the same. It's just that one is for a static case that has a friction coefficient for a static case, and one is for a kinetic case that has a friction coefficient for a kinetic case. Sometimes they might ask you for the definition of static frictional force and kinetic frictional force. So for static frictional force, it's defined as the force that opposes the tendency of a stationary object relative to the surface. So it's the force that opposes the tendency of motion. This object is not motion, it has the ability to move. And that's what the tendency of motion means. Of a stationary object, so the object is not moving, and it's always a force that's relative to the surface. So now let's look at kinetic frictional force. The definition for kinetic frictional force is defined as the force that opposes the motion of an object relative to the surface. So this one is different because it's not talking about tendency of motion or stationary object. It's saying it's opposing the motion of a moving object relative to the surface. So that was frictional force. Now let's look at another case. Let's say the surface is slanted. It's not flat anymore. There's a certain degree. Let's make it 30. And there's a same box resting on it with the same mass. So I'm just gonna draw a line here to indicate that the box is on an incline. So what forces do we have acting on it? Well, let's start off with weight. Weight is always pushing the object that has mass downwards. There's a normal force that is perpendicular to the surface. Pulling it upwards. In this case, slightly to the left because of the slant. Remember, it's always perpendicular to the surface. And logically, we know that this box, if it's on an incline like this, should be slipping down the incline. So there's a frictional force pushing it upwards. So let's say that there was a force pulling this object upwards. Well, in that case, that means that the object, if it overcomes frictional force, will move in that direction. And if it moves in that direction, that means that this frictional force will act in the opposite direction, since it opposes motion. So it will act downwards, pulling the object down as it goes up. If the object was falling down, the frictional force will be pushing it up as it tries to go down. So we have our frictional force, our normal force, our weight, and the applied force. So let's say that this applied force was being pulled up by an inextensible string connected to a pulley, frictionless pulley. And let's say there was another weight applied on it, another object. Let's say it has its own mass, which we'll call M2, and we'll call the object M2. Now they usually state that this string is inextensible. That's one of the ideal cases that they use to simplify the maths so that you don't think of the forces that might get applied and released in a elastic case. They usually assume that this string cannot be extended, therefore we don't take into account any effects of the string. And they usually state that the pulley is frictionless, so we don't take any accounts of the effects that the pulley could have on the system. So if we have this, they might ask you to draw a free body diagram of, let's say, mass 1, this mass here. So basically this is going to let us analyze what is happening on that mass there. We already have a couple of forces that we are aware of acting on that object, which is again weight pulling it downwards, the normal force perpendicular to the surface, frictional force, pulling it back, and another force pulling it upwards. That force is caused by this attachment on the string. That force is usually denoted by T. T represents tension. So whenever the string is involved, there is tension on that string. And that tension is simply the force that is exerted by the string on the object. So we have here our normal force N, our weight W, our frictional force F. And we could also, for analysis, state the angle which they might give to us in the question, the angle of inclination. So this, if we draw a dot here, is called a free body diagram. So if they ask you to draw a force diagram, you include the body, which in this case is a box on an incline, and you state all the forces acting on the body. So the weight of the mass pulling it down, there's a normal force that's going to be pushing against it. There's going to be frictional force trying to drag it back. And there's going to be an applied tension trying to pull it up. Weight, friction, normal, tension. This is called a force diagram. In a free body diagram, you just indicate it by a dot, and you have outward arrows instead of inward arrows, or normal case analysis of the forces, you'd have them outwards. And what this allows us to do, a free body diagram, is analyze the net forces that are acting on the object represented by that dot. Makes life much more simpler. So let's look at object 2, M2. If we had to draw a free body diagram for that, we'd put a dot. We know that weight is acting on the object since it has a mass. And W. And we know that it is held by a string that has tension. As you can see, there's no normal force here, there's no frictional force because it is not resting on a surface. You need a surface to have frictional force and normal force. So that's M2. M2's free body diagram. Let's get into some questions so that we can analyze and apply typical questions that we might get with these type of problems. Because the rest from this point on is just maths in a Cartesian plane. That should clarify everything that we learned here.